The last thing we're going to look at then is something called the standard error of the estimate, where what we're taking here is the square root of the unexplained variation divided by n minus 2, which hopefully looks pretty familiar because we've seen terms like this a bunch of times before. Essentially, what we have in this case is something like the standard unexplained deviation. It's another standard error, standard deviation type term, but in this case, specifically looking at it through the lens of regression and how far off our regression line is from the data set. So, if things work the way we wanted to, if our model was successful in the way that we hope, then this value here, the standard error of the estimate, would be small. It would tend towards 0, though obviously the closer it gets to 0, the more ideal our values are, and really the less useful regression is for the same sorts of reasons that I've talked about in the ideas of datasets not being or being particularly linear. Better this is to 0, the less we need to regress. But to finish ourselves off with some more understanding here, with some more sense of how this works, we're going to go one last time at the GDP and CO2 data. So, for the data regression line in the context of the GDP and CO2 emissions data, we want to find the standard error of the estimate, where, in order to get the standard error of the estimate, much like getting standard deviations way back when, you can do this the long way if you really want to, where you're going to find all those deviations and square them and take their sum and divide by things and square root the whole thing. And that's always sounded like a great big pile of fun to me, but I would completely understand if instead you want to use a calculator function. And thankfully, the linear regression t-test function is one of the ones that can get this for you. It's a bit funky using a t-test function if you're not going to actually run a t-test, but I find that that's my favorite for dealing with these things because it does all of the stuff that we need in one fun, compact step. So if you run through that computation by hand, or if you have your calculator do it for you, whichever works, what you're going to end up with for that standard error SE is something like the square root of 161,165.0546 divided by n minus 2, which is still 8, all under that radical, like I said, for a value of approximately 141.935. Where it's important here to understand what that 141.935 represents. As our standard error of the estimate gets smaller, in the same way that as a standard deviation, getting smaller means our data set is closer to a mean. In this case, instead of having something horizontal like a mean would be, we're getting closer to that maybe diagonal line. We're getting closer and closer to that trend line, that regression line, as SE gets small. And in this case, it looks like SE is pretty big. And in particular, if we want to interpret what this says, we could say something like the standard error of the estimate of the carbon dioxide emissions for a specific GDP, if we were to just take one GDP in there, would be about 141 million metric tons. Again, seems like a massive, massive number, but you have to remember that when we're looking at those values for Y, the smallest one we have is above 250 million. So the fact that we're getting something smaller than any of our data points indicates that we're actually doing okay. You know, it's not great. Obviously, we'd like that standard error to be smaller to tell us that our model is more useful, more compact, more close together, but as you've seen with all of our other measurements, all of our other computations, this is actually pretty good. And we'll talk about that more with some examples from the homework that you'll see, and maybe some more stuff in class as you'll get practice with this. Just bear in mind that even though that's a pretty big number, all things considered, for this, it's actually pretty good. But that's our last example for the semester. And other than some stuff with calculators and whatever may go on in class, this is the last video I'm making for the semester. Last one you're going to be seeing my face anyway. So, under the circumstances, I think it bears saying thank you to everybody for sticking around this long, for all of your patience and being here through this semester. Good luck finishing your homework assignments. Good luck with your quizzes, with your exams, not just for this class, but for all of your classes. I know that as much as I'd like to believe everyone here is only focusing on stats, you guys do have other things you have to do. But, anyway, it's been a pleasure working with you. Good luck. Maybe I'll see you around, maybe not, but thank you for your time.